Right, so today we're going to look at Zen3, or what Zen3 will be, or what I think Zen3 will be. Actually, we're just going to look at Zen2. We're going to look at the main weakness of Zen2, compare this to Skylake and Sunny Cove, Willow Cove, and making a logical conjecture about what changes I expect to see in Zen3. So usually when we talk about Zen2, particularly versus Skylake, is one of the weaknesses that always gets brought up, of course, is the latency, memory latency, intercore latency, and sure, memory system performance is absolutely critical to any modern processor. In Renoir, for example, the tighter Infinity Fabric gives you tighter memory latency, and the performance per core actually goes up. But it's important not to lose sight of the fact that your memory system is powering a core, and that core needs to be powerful as well. It needs to be able to keep up with the memory system. So it's important not to overlook that. And this is something that is actually overlooked in Zen and Zen2, is that the core is designed in a slightly different way than Intel did in Skylake and Sunny Cove. And the basic summary of this is that Zen has a very wide backend. So the execution units down here, we have a lot of execution units. We have on the integer side we have 7 execution paths here, and then on the FP side we have 4 execution paths. This contrasts to in Skylake and Sunny Cove, Willow Cove. They're basically the same in the math part of the execution units. We have the same setup, or we have the same setup between Skylake and Sunny Cove and Willow Cove, more or less. And we can see this portion is actually much narrower. The rest of this is mostly to do with data movement. In Zen, of course, the data movement is handled here, but you still see that the ALUs here, there's 4 of them, and then 4 for floating point here. So we have 7 independent data paths we can use for executing code, for doing math. But in the case of Skylake and Sunny Cove and Willow Cove, we only have 4 execution ports we can use for that. So really, Zen has a really wide backend, and the result of this is it can actually do a lot of calculations in each clock. But one of the weaknesses, or one of the weaknesses they designed into the architecture, was that Zen has quite a narrow instruction queue. So here we have the instruction queue. This is it's only 20 deep in Zen2, compared to in Skylake, the instruction queue is 50 deep, and it's retained the same in Sunny Cove. And this has a big impact on certain types of code, but not on others. And this is why we see some aspects of performance. Zen2 will perform very closely to Skylake and Willow Cove, but in other aspects of performance, Zen2 will fall quite far behind. Furthermore, the retire queue, or the reorder buffer, is quite shallow in Zen2 at 224 entries. This is the same as Skylake, but of course you have to keep in mind Skylake clocks a lot faster, and in Sunny Cove it's 352 entries deep, so it's a much deeper reorder buffer. And we'll go through exactly what this entails in terms of how the processor works. Lastly, the thing to keep in mind is that also the decoder in Zen2 is narrow. It's only 4-way, and even on Skylake, Intel had a 5-way decoder, which was then again retained into Sunny Cove. So really the differences amount between these two architectures to the fact that Zen2 is very wide on the back end, while Skylake and Sunny Cove are quite powerful on the front end. And again, like I said, this has implications because it means that in certain benchmarks, certain applications, you will find that Zen2 performs very well, but in other ones it performs very weak. So the first case of this kind of performance difference between these two architectures, or between Zen2 and Skylake and Sunny Cove, is that Zen2 and Zen1 actually as well has very good SMT performance, or this perceived SMT improves your multi-core performance a lot. And the reason behind this is mainly just the wider backend. We can do a lot more math in the backend because we have 7 execution ports that can all, in theory, be working at the same time. Skylake has a narrower set of execution ports for doing actual math. So when we enable SMT, obviously without 2 threads per core, the backend is always going to be starved because it's just not going to get enough enough micro-ops to get to fill up the core. But when we have 2 threads, then we can start filling up the backend much more, fill up the execution units, use them every cycle, and now our performance goes up. And because Zen2 has a wider backend, it means that we can get more performance out of 2 threads than otherwise. But the flip side of that is that when you're only running 1 thread per core, Zen2 basically has wasted execution units that are just going to be sitting idle. Of course, Skylake and Sunny Cove will have this as well, but there's many more of them on Zen2, and so you will have equally more of them will be idle. The second aspect of performance-wise is that Zen2 has very strong in-order performance. As I said before, Zen2 has quite a wide backend. So, assuming we can fill all the instructions, or fill all the execution units, Zen2 is going to perform quite well compared to Skylake, and even compared to Sunny Cove. This is caused by the shallow instruction queue and the short out of order window. But the problem with this is that because of the shallow instruction queue and because of the short out of order window, Zen is quite weak at extracting in the instruction level parallelism from code when there's a lot of dependencies. And the reason is the reason this is the case is because the way these out of order processes work is we read in our instructions into the instruction queue. In the instruction queue, we can pick the instructions that we are going to execute in the next cycle. We don't actually need to pick them in any order, apart from the fact that we can't really continue with an instruction that depends on some output of a previous instruction. So ideally we're going to pick instructions that are not dependent on some output that hasn't been generated yet. If it's dependent on some instruction that we've already done quite a few cycles ago, and we know that instruction has its results ready already, then we can obviously pull in new instructions. But if we have 2 instructions right one after the other, and the second one depends on the output of the first one, we're going to have a problem because we're going to have to wait many cycles for the first instruction to complete. Obviously we can actually push this instruction down into the deeper into the front end and into the back end, but we'll still have the problem that that instruction is going to have to wait at some point because especially when doing more complex math, particularly the floating point units, take quite a few cycles to operate. Something like 7 cycles for certain operations is not unusual, and if it even divide, in the case of Skylake, I think it was 90 something cycles. So if we have some dependency from one instruction to the next, we need to go further, we need to look further forward in the instructions to find one where we don't have a dependency. And if we have a lot of dependencies back to back, we might find that the next dependency is too far forward that the processor can't actually find it, because either the instruction queue will be full, or the out of order window. We'll already have put all of the instructions that we can down into the back end here into the reorder buffer, and once the reorder buffer is full, we need to wait to finish one instruction to kick one out of the reorder buffer, and the time when we can kick the instruction out of the reorder buffer is really when we complete the instruction, and we can say this is the final result of this calculation. So when we have the longer reorder buffer, in the case of Skylake, obviously that's the same, but in the case of Willow Cove, it's much deeper, and our instruction queue is also deeper, so we can pick instructions that will satisfy our dependency better, and when we have dependencies, we can put more of them into the reorder buffer and have them wait there for the next results, or for the results that they're dependent on to be produced. And so because of this, when we're running code that has long strings of dependent instructions, Zen is going to get stuck in the instruction queue and in the reorder buffer or the retire queue. And Skylake is obviously faster, so it's going to get through stuff quicker. So it's not, it can get away with having the same reorder buffer, or it's going to get more performance out of the same reorder buffer. And of course, Willow Cove is much deeper. It's 50% deeper, almost, and because of that, it's going to be able to look, further forward into the code to find some independent instructions to queue up. And in these cases, when this happens, Zen2's backend is going to be even more underutilized, while Willow Cove in particular can continue feeding down instructions into the backend and continue executing them. Now obviously, when we're running code which is uniform with little dependencies, we don't actually need to look very deep into the instruction queue to find instructions which are independent, and we end up rated by we end up limited by the rate that we can dispatch. We can push decoded micro-ops into the backend, and this explains in part why Sunny Cove can perform better than Skylake without having without adding more execution units. We can basically we're finding more instructions which we're pushing to the back end. And lastly, Zen has a weaker decode performance, and Zen and Zen2's decoder is four instructions wide, so we can take 4 instructions every clock, 4 macro-ops they're called technically, 4 of them per clock, and we can decode them into the micro-ops, which then we can send down into the backend. In Skylake and Sunny Cove, the decoder is 5 wide. So when we're going through code that we need to decode, Skylake and Sunny Cove are going to come out on top because they have a wider decoder. Now, the flip side of this is that there is the operations cache, and in the case of loops and repetitive code, this cache is actually going to pick up code that's going to be that's been used multiple times, and so when we do have repetitive and sort of predictable code, our op cache can be pushing more instructions down into the back end as well. So while this is something that Skylake and Sunny Cove can do as well, in these cases, again, Zen is going to come out ahead because of its wide backend. The backend can take more instructions, more micro ops, because it has more execution units and it can get through more math. So, for example, in rendering tasks, these are quite repetitive normally. Zen2 performs quite well. For example, Blender, Cinebench as well. But certain games, web browsing, and other code where it's not very repetitive, or the repetition is in such a large scale that the processor has trouble caching this in the op cache, we get bogged down on the fact that we have an error decoder. And so in general, what we see is that when we have hard to find instruction level parallelism, we have code that's not very doesn't contain many loops, or doesn't it was quite random, the code unpredictable, and then Zen2 is going to have trouble with it, Zen1 as well. But if we're doing tasks where it's repetitive, stuff like rendering, Zen2 is going to perform extremely well. And so obviously the question we started with is, what do we expect to see in Zen3? The first thing I expect to see is this instruction byte queue has to be lengthened. Secondly, I think adding a longer reorder buffer, same as was done with Sunny Cove, is going to help a lot, because AMD obviously will want to compete as well in the laptop market, where a lot of the tasks that are more important, we're talking about stuff like these Excel tests, web browsing, and stuff like that. These are tasks where there's not much instruction level parallelism, or it's hard to find, and so we need to rely on having a bigger out of order window to be able to feed the backend properly. And lastly, I'd say we want to have a 5-wide decoder. Basically, at the end of the day, we're just going to match what Sunny Cove has, and then stick that on top of the already wide backend that we have. Now, I'm not saying that we can't widen the backend more. There's quite a possibility that AMD decides to do that, and that would add even more performance in the other rendering type applications. But even without adding more execution units, beefing up the front end of Zen2 will definitely increase the performance. And I saw in a recent video, Red Gaming Tech mentioned that he thought it was down to branch predictors, and this isn't really the case, because branch predictors are extremely accurate already. Like typically, I think we might see like 1 in 100 or 2 in 100 maybe branches be mispredicted, maybe even less. So if you average that out, say 1 branch, you might lose, I don't know, let's look at worst case scenario, we're doing divides and stuff like that. We might lose 90 cycles, but if we have 1 branch every every, I don't know, every 100 cycles, and we lose 100 cycles each branch. Now, each time the branch mispredicts, obviously we're only mispredicting 1% at the time, so actually we're only losing 1% performance on the branch predictor. Or if we had a perfect branch predictor and we never mispredicted, that would only benefit us in 1% of the cases. Now, obviously, again, that's not saying that they can't improve the branch predictor. They might. There's a lot of work, I think, being done recently, but AMD's branch predictor is also quite advanced, so they might actually keep it, and they might actually focus on these other aspects that I've been talking about. So I think overall I would expect Zen3 to look at improving the performance where it's currently at a deficit relative to Skylake and Sunny Cove. And this is irrespective of the memory performance. This is the performance of the core itself. Tasks where Zen2 already performs well, we might see smaller gains. Zen3 would end up being quite a bloated core, like Sunny Cove and Willow Cove are, but it's on 7nm plus. Apparently they're getting more density in the new nodes, so they've had to put the transistors to use somewhere. So, yeah, I think that covers it. I hope you learned something. If you have any comments or suggestions down below, just post them, and I guess I'll see you in the next one.